Winglets have become one of the most recognizable features of modern commercial aircraft. From narrow-body workhorses to long-haul wide bodies, these vertical or angled extensions at the tips of wings are widely associated with improved fuel efficiency and lower emissions. Airlines promote them as part of their sustainability efforts, while manufacturers highlight their aerodynamic advantages. So in this video, we take a look at how winglets work, how much fuel they really save, and whether they truly make the biggest difference on long-haul routes. Winglets are rooted in a fundamental aerodynamic challenge. Aircraft wings generate lift by creating a pressure difference between their upper and lower surfaces. At the wing tip, high-pressure air from beneath the wing naturally flows upward to the lower-pressure region above, forming swirling vortices. These vortices represent wasted energy and create induced drag, which forces engines to burn more fuel to maintain performance. Winglets are designed to reduce this effect. By extending upward or outward from the wing tip, they disrupt and weaken these vortices, improving the aircraft's lift-to-drag ratio. The result is a more aerodynamically efficient wing that requires less thrust and therefore less fuel. Under optimal conditions, this can reduce fuel consumption by up to 5%, with the added weight of the winglet offset by the efficiency gains during cruise. Modern winglet technology can be traced back to research conducted by NASA in the 1970s. In response to the 1970 oil crisis, improving fuel efficiency became a priority. At NASA's Langley Research Center, engineer Richard Whitcomb developed and tested the concept of vertical wingtip devices. His work demonstrated a 7% improvement in lift-to-drag ratio and a 20% reduction in induced drag. These findings laid the foundation for modern designs such as blended winglets, which integrate smoothly into the wing structure. Over time, this technology has delivered substantial real-world benefits, saving billions of gallons of jet fuel and significantly reducing carbon emissions across global airline fleets. While aerodynamic theory explains why winglets work, operational data shows how much they actually deliver. Across a wide range of aircraft and routes, winglets consistently produce measurable fuel savings, though the scale varies considerably. On average, aircraft equipped with winglets consume about 3.45% less fuel than those without them, according to Cirium. However, the range of outcomes is broad, with savings varying from roughly 1% to as much as 10%, depending on conditions. In practical terms, most aircraft see typical improvements in the 4 to 6% range. Aircraft type plays a major role in determining these results. The Boeing 737-800 is one of the strongest performers, with efficiency gains averaging around 6.7% and reaching over 10% on certain routes. The Airbus A319 tends to deliver more consistent, predictable improvements, while the Airbus A321 shows a wider spread of outcomes depending on configuration and mission profile. Real-world airline experience reinforces these findings. Aircraft such as the Boeing 737-700 equipped with blended winglets have been reported to save approximately 100,000 gallons of fuel per year per aircraft. In addition to fuel savings, these winglets reduce carbon dioxide emissions by up to 6% and nitrogen oxide emissions by around 8%. Noise reduction is another benefit, with some configurations lowering noise footprints by more than 6%. Route length is the single most important factor in determining how effective winglets are. The reason is straightforward. Winglets provide the greatest benefit during cruise, when induced drag is a constant factor. The longer an aircraft spends in this phase of flight, the more opportunity there is for fuel savings to accumulate. On shorter routes of around 500 nautical miles, the benefit of winglets may be as low as 1%. In these cases, the added weight and structural complexity often counter much of the aerodynamic gain, particularly because the aircraft spends less time in cruise, where winglets deliver the greatest cumulative benefit. As route length increases, the equation shifts. On medium-haul flights of approximately 1,000 nautical miles, fuel savings typically rise to between 4 and 5%. On long-haul routes exceeding 3,000 nautical miles, savings can reach 3.5% or more, with total reductions often falling within the 4 to 8% range for larger aircraft. On long-haul routes, winglets do more than reduce fuel burn. They can influence how airlines operate their networks and compete in the marketplace. Because fuel is one of the largest operating costs for airlines, even small percentage savings can translate into significant financial advantages when applied across large fleets and long distances. One of the most important benefits is extended range. Reduced drag allows aircraft to fly farther on the same amount of fuel, enabling airlines to operate non-stop routes that might otherwise require a refueling stop. This capability is particularly valuable in intercontinental travel, where direct flights are highly attractive to passengers. Today, the ultra-long-range aircraft on the market tend to feature raked or swept winglets, like on the Airbus A350 and Boeing 787, which seem to fade into thin air but are incredibly efficient. Winglets also improve payload flexibility. By reducing fuel requirements, airlines can allocate more weight to passengers or cargo, increasing revenue potential on each flight. Over time, this can enhance route profitability and support more efficient fleet utilization. In addition, winglets contribute to quieter operations, which can be important for airports with strict noise regulations. This allows airlines to maintain access to key markets while reducing their environmental footprint. Despite their clear advantages, winglets are not a universal solution. They introduce additional weight and structural complexity, which can partially offset their benefits. Maintenance requirements may also increase as winglets add stress to the wing structure and require regular inspection. Different designs involve different trade-offs. Blended winglets offer a balance between aerodynamic efficiency and structural simplicity, while more advanced configurations such as split-scimitar winglets provide greater drag reduction at the cost of increased complexity and weight. Each design must be carefully matched to the aircraft's characteristics and operating profile. Because of these factors, winglets are most effective when integrated into the aircraft's overall design rather than added as a modification later on. Their performance depends on how well they align with the aircraft's aerodynamics, mission profile, and operational environment. From an industry perspective, organizations such as the International Air Transport Association recognize winglets as an important component of aviation's broader fuel efficiency strategy. Alongside more efficient engines, lighter materials, improved flight planning, and sustainable aviation fuels, winglets represent one of many incremental improvements that collectively drive meaningful reductions in fuel burn and emissions. Winglets do significantly reduce fuel burn on long-haul routes, but their effectiveness depends on context. The aerodynamic principles behind them are well established, and decades of research and operational data confirm their value. On long-haul flights, where aircraft spend extended periods in cruise, these benefits are amplified, delivering meaningful reductions in fuel consumption and emissions. At the same time, the impact of winglets is not uniform. Route length, aircraft type, and design all influence the outcome, and their advantages may be limited on shorter flights. They also introduce trade-offs in terms of weight, complexity, and maintenance that must be carefully managed. Ultimately, winglets are a proven and valuable tool in modern aviation. They are not a standalone solution, but when applied in the right context, particularly on long-haul routes, they provide clear and measurable benefits that enhance both efficiency and operational performance. What do you think? Do you see winglets as one of the most important efficiency upgrades in aviation, or just one small piece of a much bigger puzzle? Let us know by leaving a comment, and don't forget to subscribe for more aviation content. See you next time. In addition to our daily YouTube videos, Simple Flying publishes over 150 articles and a podcast every week. Visit simpleflying.com.